Lake Mead has fallen 140 feet since the year 2000, and nothing, no policy, and no emergency measure has reversed it. Hoover Dam was engineered to deliver 2,080 megawatts from 1,229 feet of hydraulic head. Today, the reservoir sits near 1,040 feet, but the missing water isn't the full crisis. Built into this dam are critical elevation thresholds, and as the surface drops past each one, the economics of power for over 1 million people fundamentally shift. At the heart of the Colorado River system, the numbers are carved into concrete and steel. Lake Mead's full pool sits at 1,229 feet above sea level, the high water mark reached in the 1980s, when the reservoir brimmed with 27.6 million acre-feet of water. That was enough to supply tens of millions of people, irrigate vast agricultural valleys, and keep Hoover Dam's turbines spinning at full power. By the year 2000, the surface had already slipped to 1,182 feet, marking the start of a slow, relentless descent. Today, the lake hovers from 1,040 to 1,045 feet, a visible drop of 140 feet, exposing once submerged canyon walls and leaving boat ramps stranded far from the water's edge. The iconic white bathtub ring traces every foot of loss, each layer a silent record of drought, overuse, and shifting climate. But beyond the shoreline scars, the real significance lies in the invisible thresholds built into the dam's design. Hoover Dam's operation is governed by a series of elevation markers. At 1,182 feet, the system can meet every delivery and power contract. Below 1,150 feet, the first operational constraints begin. The 1,050-foot line is more than a round number. It is the edge of the minimum power pool where the dam's turbines start to lose efficiency and risk mechanical stress. If the lake falls to 1,025 feet, the efficiency curve takes a sharp downturn. Turbines designed for a high hydraulic head now struggle with reduced pressure, forcing operators to throttle back generation and increasing the risk of cavitation inside the machinery. The dam's lowest threshold is set at 950 feet. This is the minimum elevation for any power production. If the water drops to 895 feet, known as the dead pool, gravity can no longer move water through the dam, and both power generation and downstream releases would cease. These lines are not just technical footnotes. They are operational boundaries that dictate how much water can be delivered to farms, cities, and industries across the Southwest. Every foot of lost elevation translates into a measurable loss of storage. At full pool, Lake Mead holds enough water to supply Las Vegas for nearly a decade, or to irrigate the entire Imperial Valley for more than 2 years. Now, with only about 40% of its capacity remaining, the margin for error has narrowed. The math is simple, but unforgiving. As the surface drops past each threshold, the system's ability to deliver on its promises diminishes, and the pressure on every downstream user intensifies. These elevation lines, once abstract engineering targets, have become the hard limits shaping the future of the American West. The relationship between water and power at Hoover Dam is governed by simple physics, but the consequences ripple across millions of lives. As the surface of Lake Mead drops, the hydraulic head, the vertical force that drives water through the dam's turbines, shrinks in lockstep. For every foot of lost elevation, the dam's output falls by about 4.5 megawatts. Over the past 2 decades, that decline has erased more than 600 megawatts from Hoover's original 2,080 megawatt nameplate capacity. In 2023, the dam generated just 2.8 terawatt hours, down from a historic average of 4.2 terawatt hours. This loss is not a matter of flickering lights or idle turbines alone. It is a shift in the foundation of the Western power grid. Hydropower from Hoover is among the cheapest and cleanest sources available, historically delivered at around $30 per megawatt hour. When low water cuts into that supply, grid operators must turn to natural gas peaker plants, which cost between $55 and $70 per megawatt hour, and pump additional carbon into the air. During peak summer demand, when air conditioners run non-stop and the grid is stretched thin, the gap left by Hoover's missing megawatts drives up wholesale prices, sometimes by 15 to 20%. The Western Area Power Administration, called WAPA, manages Hoover's output and contracts with more than 1 million direct beneficiaries, cities, water agencies, tribal utilities, and rural cooperatives across Nevada, Arizona, and Southern California. Every shortfall in hydropower requires these customers to buy more expensive electricity on the open market. For many, especially small towns and agricultural districts, the difference is not academic. Annual retail rates have already begun to climb, with 3 to 4% increases projected through the decade as hydro output declines. A grid planner from WAPA describes the challenge this way: hydropower is our backbone resource. When the lake drops, we lose flexibility. We have to replace that with something less reliable and more costly. The numbers bear this out. Each foot of decline is not just a visual marker on the canyon wall, it is a direct subtraction from the region's energy security and economic stability. The lost water means lost power, and the cost of that loss is measured in dollars, emissions, and the resilience of the Western grid. As Lake Mead's decline continues, the system grows more exposed to market volatility and extreme weather, with fewer tools to manage surges in demand or sudden outages. The dam's original promise of abundant, affordable power is now constrained by the very climate shifts it was never designed to face. The arithmetic of the Colorado River Basin reveals a problem that cannot be solved by engineering alone. In 1922, 7 states signed a compact dividing the river's flow into 2 equal shares, 7.5 million acre-feet per year for the upper basin and 7.5 million for the lower basin. Later, a treaty promised another 1.5 million acre-feet to Mexico, bringing the total to over 16 million acre-feet claimed on paper. But the river itself rarely delivers that much. Modern measurements show the true average flow hovers around 12 million acre-feet per year, a shortfall of more than 4 million acre-feet baked into the system before a single drop is released. Lake Mead was built to buffer these swings, with a maximum storage capacity of 26.1 million acre-feet. Yet the gap between legal promises and physical supply has only widened. Over the past 2 decades, the basin has endured the driest 20-year stretch in at least 1,200 years, confirmed by tree ring records stretching back to the Middle Ages. Snowpack feeding the river has dropped by 30% since the late 20th century, and rising temperatures have increased evaporation and reduced runoff. The result is a structural deficit. Every year, more water is promised than arrives, and the reservoir's storage continues to shrink. This imbalance is not a temporary drought. It is the arithmetic of scarcity written into law and climate alike. Mandatory water cuts now follow a strict federal schedule, triggered as Lake Mead's surface drops below set elevations. In May 2022, the Bureau of Reclamation declared Tier 1 after the reservoir slipped under 1,080 feet, forcing Arizona and Nevada into their first compulsory reductions and activating Mexico's treaty cuts. By May 2024, Tier 2 arrived as the lake crossed 1,050 feet, deepening cuts to 8% for Arizona and 5% for Nevada, while California faced pressure for voluntary savings. A draft Tier 3 circulated in April 2025 outlines even sharper curtailments if the water level falls to 1,025 feet, a point where the system's basic function is threatened. A Bureau official calls it managing scarcity by statute. For Las Vegas, the response is engineering. Plans for a third straw intake, reaching nearly 150 feet below the current structure, aim to keep water flowing even as the lake nears dead pool. The retrofit, projected at $3 to $5 billion, includes a deep tunnel and advanced controls. The Southern Nevada Water Authority's manager warns that without such investment, the city's supply would be left to chance. Yet each new tier and costly fix only buys time, as the gap between supply and demand remains. The financial toll of Lake Mead's 140-foot decline ripples outward in hard numbers, not just lost water. For the Imperial Valley, where rows of lettuce and alfalfa once stretched to the horizon, the cutbacks now cost farmers $1.2 billion in annual crop revenue. Each acre that goes unplanted means fewer paychecks for field workers and less business at the local feed store. At the same time, the region's tourism economy has taken a $250 million hit. With marinas closed and once busy boat ramps stranded above dry gravel, fewer visitors come for fishing trips or lakefront weekends. Hotel bookings and restaurant sales have slumped, leaving small towns to shoulder the loss. Across the seven-state basin, these shocks add up to 12,000 jobs at risk, from farmhands and irrigation crews to hospitality workers and equipment suppliers. An Imperial Valley farmer puts it simply: when the water drops, everything else follows. Jobs, families, the whole town. This new reality stands in stark contrast to the optimism of 1935, when Hoover Dam opened with the promise of endless water and power. Back then, planners assumed a river that would always deliver. Today's numbers tell a different story. The economic consequences of a shrinking reservoir are no longer distant threats. They are annual losses measured in billions that challenge the very model of growth the West was built on. The question now is whether adaptation can keep pace with the scale of change, or if a more fundamental transition is already underway. Today, every foot Lake Mead drop and redraws the mathematics of life in the West. Less water, fewer megawatts, higher costs. The real question isn't how to reclaim the past, but whether the region will adapt to a permanently smaller river. What does sustainability mean when the baseline itself has shifted?